I'm Sunile Manjee. I'm a senior principal solution architect at Elastic. I specialize in vector search and generative AI. And, as I like pain, so recently I started working with Databricks. This is not Databricks company, but I actually, my background's in Apache Spark. I was a contributor for a while. And then my buddies obviously are Databricks. I went to Elastic. And then we decided, why don't we just do an academic project to build an LLM? You can talk to me after. I can tell you all the pain that, and it's called Blue Sparrow. Hopefully it will be published by the end of June, but right now there's a lot of politics. But anyways, a lot of this I'll share with you, like my lessons learned, because I wanted to understand why. And so vector search, and it's just, all of it has everything to do with, if you start to understand how a model reasons, then the light bulb went off for me. So you may already know this, and congratulations, but I had to actually work through a model and actually build one. And ours is going to be around 35 billion to 36 billion parameters. So not as big as, Mistral's 80, but ours is based on Mistral 2 billion. All right, let's get to it. So let's talk a little bit about search, okay? When you search for, wherever you search for, let's take an example of you going on a website and you're searching for F-150. Your expectations are that you want an F-150 to show up, right? There's no semantic interpretation of that. In fact, it would kind of piss you off if it was semantically interpreting it, right? And so it was interesting. There was an interesting conversation I had with someone at the World's AI Engineering World's Fair. And someone was like, hey, I think we should always semantically interpret everything. I said, okay, let's have a conversation. And let's try to semantically interpret everything we say to each other. And I didn't even have to start the conversation. He's like, yeah, this is a bad idea. I'm like, exactly. Not everything needs to be semantically interpreted. So this is an example. When you're searching for something precise, you want it to return that. However, it does absolutely make sense when you need semantic interpretation. So for example, if you're looking for a pickup truck, you expect a Ford F-150, a Silverado. By the way, I'm from Texas. I'm a big truck guy. So hence here, though I don't see many in California for, I can see obvious reasons. So, so that's what you expect, right? But, I was working with a customer, and the third swim lane, he actually made me change because he said, Sunile, this is too cute. You got to make it more complicated. So he gave me a query. Now, I had to change it to pickup trucks because that's what I was talking about. He was talking about his customers. So I convert. He said, hey, half ton. By the way, if you don't know what a pickup truck, what a type of pickup truck is, half ton is a type of pickup truck. There's full ton, 2 ton, 3 ton. Anyways, it's a type of pickup truck, right? And then you have, within there, you have a pickup truck within 50 miles of a particular zip code available as in a certain date. This literally came from a customer during a Gen AI workshop. He said, this is what my search query looks like, not the other two. Well, that's interesting. So how would Elasticsearch do this, right? So a part of this query, you have half ton. Well, why semantically interpret that when it's a part of your metadata or it's a part of your fields, right? Automatically distill that. Don't allow the graph to go figure something out. And then a part of the pickup truck is semantic. So go ahead and interpret that. Within 50 miles of a zip code, well, if you know Elasticsearch, we have a rich geospatial API. So do a bounding box and ST within. And then lastly is as in within a certain date. And by the way, I have an entire notebook published on this on my GitHub page where I show exactly this statement and how you run through NER to go parse it out and automatically inject a brand new query, right? And on my YouTube page called Data Jedi, I actually did a demo of doing exactly this. So that's what you expect, right? By the way, that's my pickup truck on the top right. So yeah, it's a TRX. So anyway, so that's what we expect. So this is what I looked like probably 6 months ago, or maybe a little more than that, where when we're like, oh, we're all using LLMs, we probably all have used ChatGPT. And then you start to go, how does it work? And you go, oh, it's magical. That's what I thought. It was magical. Of course, it's more than that. But we really, for me, I wanted to go down the exercise because I'm customer facing. I really had to make sure that I know what I'm talking about when I run into a buzzsaw of a customer where there's a data scientist in a room and he'll just ask me 100 questions. So I was like, you know what? I need to strap up. So that's why I went down the scientific experiment of building an LLM. Very painful. So how does it work? Here is how through much pain, I was like, I have to figure out a way to explain how LLMs works without going into the code, which I don't know. I don't think it's very sexy to show code, even though we're seeing a lot of that, and I'm a big coder. I'll just explain it to you in simple terms. So here's what I'm going to ask you folks to do. This is very simple, okay? I'm going to ask you to stand up and we're going to compete against a large language model. And I'm going to show you how a large language model works. So please stand up.
For reference, he had like 400 of us do this at our sales kickoff in Vegas a few months ago. So yeah.
Yeah, okay. So here's what we're going to do. We're going to see if you're smarter than a 70 billion parameter large language model. Don't worry, you'll sit down very quickly. So let's predict the next. Yeah, we'll see if you can beat this. This is pretty good. Let's predict the next word. So I'm going to give you two words, the cat, and I want you to predict the next word. And it's either going to be climbed, chased, leaped, or slept. So those of you that believe it's climbed, raise your hand. Okay, sit down. Those of you that believe it's chased, everyone else sit down. Only the ones that have their hands up, stay up. Okay, stay standing. All right. So Gemini, Meta AI and Gemini predicted it was going to be climbed, and ChatGPT predicted it was going to be slept. So they just didn't have enough context, right, to predict the next word. So let's continue. The cat chased the mouse, ball, squirrel, or dog. So now they all have a little bit more context. So those that believe it's mouse, raise your hand. Okay, whoever's not, I don't think so. Okay, well, all the models actually thought that it is actually going to be mouse, and they did, and that's actually correct. So let's do this 2 more times. The cat chased the mouse through, around, into, or under. First word is through. Who thinks it's through? Around. Take a seat. Into. Take a seat. Okay, it is under. So now we're going to do this one last time. The cat chased the mouse under the, and this is becomes very interesting, the study. And it's couch, table, bed, or stairs. Couch. Sit down.
At my house, it's couch, just so you know.
Table. You're wrong. You have to sit down. Okay, so this is what happens. You can take a seat. It is actually table, but I'll explain how this works. So, and you'll see how the model predicted this in just a moment. So what ends up happening is model prediction is all about weights and fill mass. The last stage of the multi-head is fill mass. It's always trying to predict the next word or the next token. That's all it is. So how does it do it? This is where I found it fascinating to understand this. So what ends up happening is as it goes through the multi-head, it basically has an attention activation. It basically says, what should I pay attention to? And it puts weights upon that. So it put weights upon chased, mouse, and under. And you notice how cat, it also put a weight, but it put it just less. And that to me was very confusing. I did not understand why it's not equal. And I had to fail a couple of times to figure this out. What ends up happening in a model is that it's going to say, okay, when it hits the multi-head, it basically says chase, mouse, and under. It feels that it can predict the next word without cat being a part of the equation. So it comes up with a list of tokens or predictions. And then it says, let me add cat after the fact, and we'll eliminate the things that don't make sense. So I'll make one up, like chased, mouse, under, and then let's say one of the predictions was, I don't know, just bark. I'm just gonna make something up. Cat doesn't bark, right? So, well, that's gonna eliminate it. They added chase after the fact, cat doesn't bark, and meows, gone, right? So that's how it does. And then the ones that the does, very little weight, and a lot of times, like Mistral, actually is unbelievable. Mistral is one of the only models, at least during our exercise, which it actually does not even assign a weight. It actually filters them out completely. That's why it's so fast to train Mistral versus all the other models. It's, I don't know how.
Stop word.
I'm sorry?
Stop.
It's just stop word. But the thing is, BERT doesn't do it, right? And they built it on BERT. So it's very interesting how they just added these additional classifications, and you can fill them back in. But it's pretty interesting how Mistral, if you look at the charts, even though they're not the cheapest, they're always, in training wise, they're always the fastest. It's just they're able to eliminate these words. So if you look at it, if you run it through another model, you'll actually see that it does actually have the highest percentage. So table. I'm going to go through as fast because I know we're like almost out of time. So let me talk to you about search relevancy. Elasticsearch is a search company, right? So one of the challenges is that most customers say, I'm not getting relevant results. And as a solution architect, it's you have, when I first started here, I was like, how do I even address this problem? And this is how I think about it. Whenever a customer tells I have a search problem or I have a relevancy problem, relevancy in my mind is in two stages. If you've ever done apple picking with your kids, they go and pick 1,000 apples, and you tell them, what do? You go, okay, pick the ones that are round, that don't have wormholes, and the ones that have wormholes, throw them on the ground, they become fertilizer or compost. So you have all of those, right? And then what happens in the next stage in manufacturing generally is that Whole Foods, I was actually working with a customer that told me this, that Whole Foods, because they cater to a different audience, their audience is willing to pay more for nice, bigger apples compared to like the cheaper grocery stores, right? So you go through a ranking stage. So first, you need to grab all the right apples, and then the second stage is go and rank those apples. Well, if you retrieved a bunch of bad apples, you're just ranking a bunch of bad apples, right? What's the point? So that's how I think about it. I always ask the customer, if they're saying I have a relevancy issue, is your recall or retrieval good enough? Because if it's not, what the hell are we doing here, right? This makes no sense. And we're gonna, by the way, dig into this. We're just running out of time. I can talk about search all day. And then that's what relevancy is, okay? Let's talk about vector models. I get asked the question, and I'm sure nobody in this room ever does that. What's the best vector model? I think it's absolutely ludicrous to ask that kind of question. And I know you'll never do that, but I get asked that in the field a lot. So let me explain how this works. To ask someone what is the best vector model is like thinking of it like art. So this is a representation of Martin Luther King at a point in time by 3 amazing artists, right? Dan Wilson, Suzanne Simons, and Derek Russell. Now, if I asked you which one is the best, I'm pretty sure we would all have a difference in opinion. It's based on what you like. What is your use case? Some of them may be looking for something that's more realistic. Dan Wilson always does an amazing job of that. Pastel, that's Derek Russell. That's his game, right? So it depends on the use case. So to ask a question, what is the best vector model? Why it doesn't make sense? These numbers, see, we as engineers, and again, I'm not putting him in that crowd because I don't build large language models for a living. I do it as a scientific experiment. But what I found is that if you use our Blue Sparrow model that I co-built with Databricks, you're going to find that our number representation is different than using Mistral's core models, right? Or if you use Llama. Why is that? Because that is the opinion of the engineer or the artist of building that model. And that's our representation of the world, numbers. Right? So each one of these, and obviously we don't represent it in portraits or paintings, we represent worlds in numbers. So you can't ask the question, what is the best vector representation? It really depends on the model scorecard. You have to go look at Blue Sparrow when we publish it. You have to look at the model card. What did we train it with? And that will tell you whether or not this is a good model to work with. Okay, so the other thing is, this is interesting at the conference I was just at, I overheard someone saying, I don't think, I think we just need to use vector search for everything. And I'm just nosy. So I'm like, I just walked in, I'm like, what the hell are you talking about? So I asked them this question. I asked everyone this question that thinks vector search is the only thing. Elasticsearch is a vector database, but I ask you the question, is distance the only consideration when it comes to relevance between 2 objects? Is that the only thing that should matter? You'll see in a second why. There's a reason I'm asking this. So this is not the example, but this is one example. By the way, somebody wrote this article and it was amazing, and I'm giving them credit. I stole this from them. Is basically they ran into a vector search as how can I analyze large data sets and how do I process very big data? You can see that the distance is quite low here, right? So let's walk through and I'll give you an example of how we work through the feature aspect of it. So let's talk about ELSER. So we talked about, we're not going to do much on BM25 today, but I talked about vectors. We're going to talk about how ELSER works. ELSER is a 0-shot out of domain model, sparse model, okay? And why it does a good job, I'll explain it. But basically, if you're familiar with SPLADE, it's basically based on SPLADE, okay? So let's kind of skip through what it does, but if you actually look in Elasticsearch, you're gonna find tokens and weights, or numbers, whatever you wanna call it. And oftentimes when you look at this, it doesn't make any sense. Well, there's a reason for that. Let me explain. So when you have 2 sentences, and you say, why don't you just vectorize everything? Why do we care about sparse vectors? Well, the reality is, if you look at this, and by the way, I'm a big fan of Cohere, but this is an example of 2 sentences that even though dog and cat, they're both mammals, And there's chased, and then there's squirrel. There's a verb in here, and they're doing an action to something. Yes.
I have a question. Can you do a hybrid search in Elasticsearch? So can you combine, let's say, BM25 and vector search?
Absolutely. There's a slide. There's getting to that. It's called the retrievers. Absolutely. So in fact, it's not just BM25. It's BM20. It's for this conversation, we'll say text search, vector search, and ELSER search. Okay. And you'll see what ELSER means. So you can do all three. So who gives a damn anymore, right? Like just may the best hit win. That's my opinion. Instead of fighting people in vector search, I just say, why not? Why just allow it? Now, there may be scenarios where vector search is the only thing you want to do, but it's surprising in the field where I work with the most complicated customers, and they unravel themselves very quickly, right? When they say vector search, and then you start to say, well, that was a precision hit, right? And by the way, you know, when someone says, I need a precision, I need a high precision, and low recall, meaning low recall is in the actual ranking, that's an oxymoron when it comes to vector search, because high precision does not equal KNN. It's approximate KNN. Precision is off, right? An offset of whatever's in the cluster. So you just have to ask questions and you realize people don't know what the hell they're talking about. So this is an example, right? Like if vectors are for everything, these two things are like super far apart. And I'm a big fan of Cohere, by the way. Huge fan of Cohere. And this Cohere's model said, yeah, these things are not alike. They actually are. So how is it that ELSER does this? So ELSER works on out of domain context. So how does that work? Is it magical? It's not magical. By the way, it is based on BERT, okay? And what it does is it says, okay, I'm gonna take your original statement or text, I'm gonna expand that sucker, right? And I'm gonna expand it to terms in my vocabulary, like the model's vocabulary. So it basically said, okay, and think, by the way, those of you that are familiar with Elasticsearch, think of this like synonyms, okay? But it's more than that. These are not like heuristic synonyms. These are synonyms based on the BERT model or whatever model we chose. It's a proprietary model. But it basically expanded dog to canine, pet, we'll look up there, not there. And it expanded chase to pursuit and expanded squirrel to certain things, right? So it said, okay, that's great. Then it also expanded cat to, let's say, kitty and feline and pet, and expanded dislikes and rejects and despises, and expanded mouse to rodent and rat. Okay, so what? What's interesting about this is there could be terminology in here that is domain specific. So I'll give you one example. Like when I say latitude to you, what does that mean? Right. Geo. You know what it means to Dell?
It's a laptop. Latitude is
Exactly.
you know,
They had this problem, okay?
so this is like a latent semantic.
It's an expansion, right? It's basically speaking, see, it does, BERT model will always think that latitude, unless you prompt engineer it, but we're talking about vectors now. There's no prompt engineering in vectors, right? So unless the vector model's space knows what a latitude is, you have to fine tune it, which, by the way, there's a company called OpenPipe, great company. They do kind of this kind of work, but most customers don't want to get into fine tuning. So what do? You do something like this, which is I'm going to expand the meaning of latitude. Or I'm going to expand the meaning of your domain to something it understands. So why is that a big deal? Well, first it adds weights, right? That's tokenization, right? And weights. And then it matches not on the original text. It only matches on the expansion. So this, oh, darn it. So it only matches on the middle swim lane. It says, I'm going to do this. So this is where the light bulb goes off for most customers, because they have proprietary, they have language that the model doesn't understand. So we don't try to match upon that. We match upon the expansions or match upon the auto synonym. Somebody called it an auto synonym. A customer called it that. I'm just going to leverage that, right? So that's why it's a big deal. It's pretty damn good. Okay. Now, someone would say, Sunile, I think a vector model could do better. Good. Then allow it to do better. That's why hybrid search is a big damn deal, right? I'm not here to fight you and telling you to go use only this or the text. I'm telling you, use all of it. One query, issue all of it, may the best hit win. That's my opinion, right?
How does it do the expansion?
I have a slide on that, but I think I do. I neutered this entire thing because he only gave me like 10 minutes. But
Not my fault.
so at ingest time, you just give it any text, right, or passage, and we will automatically infer it. We have machine learning nodes in Elasticsearch, and the machine learning nodes can host ELSER, which is our proprietary model, or it can host your vector embedding models, right? So we do it.
Is it basically just like you take the vector that mouse represents in this sentence and then compare it to a list of all of the vectors that you have in your BERT model. And then you say, give me the 2 that are closest.
So,
or
yeah.
5 that are closest.
Yeah, I want to make, so you said something that maybe I did a poor job of explanation. It's probably me. So like when you ingest, let's say this is your document that you have in Elasticsearch. And then you ask this is your query. So we will store this and this expansion in Elasticsearch using a sparse vector field. When you ask the question, we will take this, expand it, and then match upon this.
You're actually storing the vector, is expanded vector representation. You're not just doing it at query time.
That's, yeah, right here. See, these are the expansions. We actually store this Elasticsearch. And then when you ask a question, we will at runtime or whatever you want, at query time, we will do this on the fly. And then take this, your query, and match it against this, find the matches, look at the weights, and then you saw how the score is computed, right? We just multiply that. I just didn't talk about that because we're so late on time here. But that's how the score is computed, right? We basically multiply.
You're basically
Multiply.
like pre-indexing an expansion list that's derived from a model.
That's exactly it. Yeah, it's pretty simple. And when someone says that, I'm like, hell yeah, I did my job. So it is, it's not complicated. Okay, so one of the biggest challenges for those of you in search probably picked up on it. By the way, in the Neo4j session, there was an individual that talked about this, and I was like, wow, that's my world. What is the biggest challenge with this is when you search text search, let's say that you have a document that has Phil's name in it like 30 times. Well, and then you just search for Phil, right? Well, the score of anything that matches text search is always going to be higher than the scores that I just showed you, right? So how do you normalize this? It's hard. People are doing script scores. It's difficult. You got to normalize that stuff. So there's multiple ways to like bring all those, the hybrid query together, because each one of those independent queries, text search, sparse search, and vector search are all going to give you different scores, right? So our biggest customers are always creating their own normalization methods, but there is an easier way. I'll tell you in a second. Okay. Remember I asked you a question, is distance the only thing that matters when it comes to relevance between two points, two objects? Let me give you an example. This is where I used to live. Now I live in Texas, but I used to live in Chicagoland area. This is an actual screenshot when I went and visited my mom recently. And I'm a big Home Depot fan. And when I go to Home Depot, which one do you think I go to? I mean, the answer's right here.
The one that has the thing in stock that you want to pick up.
It's a good answer. Actually, that's interesting. We'll talk about that in the next slide. That's important. But just which one do you think I go to? Any guesses here?
1905.
1905, because it's the closest to me. Well, I don't. And the reason why is because I have a pickup truck in Chicago, and I hate when anyone parks next to me, and I hate Home Depots that have small parking lots. Okay? I do not go to Home Depot that has small parking lots. I love big Home Depots. Stock is a big issue, right? I'm a big Ryobi tool guy, and I just find that the smaller Home Depots just don't have the stock in Ryobi tools, even though it's their brand, right? So there's many reasons to it. Plus, I'm a big right turn guy because I have a truck, right? I just don't want to do it. So I love number right turns. So why am I telling you my Home Depot story? It's kind of silly, right? Well, what I just articulated to you is features, okay? So now my expectation is the next time when I'm in Houston, I live in Houston now, the next time I ask for a Home Depot near me, I don't want this application to just look at the distance between myself and the next Home Depot. I want it to look at the store size, the number of I'm just weird, the number of right turns, the parking lot, and oh, by the way, rating is big. Rating, a lot of times you will find that people like me that are big into Home Depot, we rate really bad on store inventory, right? It's just, it's a deal. It's a thing at Home Depot now. So the next time I ask the same question, Home Depot near me, I don't want you to just think about the distance. I want you to think about all of these features. So now I ask it, why is this important? Because we have something called learn to rank. What happens in learn to rank is that now that I've created a behavior, I selected the second one, and there's things a part of that store, like parking lot size, all these things are features. The next time I ask this question, it went into the judgment list. The next time Sunile asks that question, it will give me the Home Depot that's not only nearest to me, but it takes this into account, and my expectation is that will be at the top. Yeah.
First of all, I don't think you're weird about the number of right turns because I feel you on that one, but
Thank you.
you skipped over the part about how it knew why you picked Woodbridge.
Why? Oh, why? Okay, so
You
it's,
picked, you picked Woodbridge because you know something,
yes.
but how does the app know that you picked it on those features? There's no way for you to input that information.
So in the data set itself, in Elastic, let's say you have documents, right? So it's gonna have, for example, part of Home Depot, it's gonna have these attributes a part of it. And each one of these attributes, when you go to learn to rank, it's a supervised model. It tries to understand my behaviors and which one was it, like, for example, if it tracked me from, I consistently selected Home Depot, this one, and like 4 others, okay? And these seem to always be reoccurrent in the network. So it says, okay, these are more dominant in terms of weight. So next time Sunile asks, that's what's gonna come up. So it has to happen a few times. So these attributes are just within the document. It just occurs more frequently because of those documents. And we have a whole notebook around the weights and how it automatically determines it. And by the way, it uses XGBoost, which is all weighted, right? So just over and over again, as I go to Home Depot with right turns, bigger store, that weight of that particular node in XGBoost just becomes fatter and fatter and fatter, and then that's the one that we're gonna select. It's not rocket science, it's pretty simple, right? I wish I could tell you we're doing something cool, but it's not. It's pretty easy. We're just features, XGBoost, we're done. Oh, the notebook, by the way, okay? And I have another one that talks about Home Depot as well. And I have a YouTube video on the Home Depot scenario. Weird, but this is how you would do it. So you just basically ask a query again, and then and this time what you say is, I'm asking the same query like Home Depot near me, but this time we're gonna say have the model make sure that, and don't give Sunile just distance, give Sunile based on his past behaviors. Semantic re-rankers, we're almost finished. I know you want to go home. Semantic re-rankers are basically third level re-rankers. So I showed you level 1 re-ranker, which is how many times do you see Phil in a document? That's pretty simple, right? You see him 100 times in a particular document, that document should come up first. The second level re-ranker is learn to rank, which is a supervised way of doing it, like looking at my behaviors, looking at the features, and then the next time you ask a question, that should come up. This is unsupervised. And by the way, these are not mutually exclusive. You can run through all 3. And what's semantic re-ranker is basically saying, okay, I'm gonna run through Elastic, whether it's LTR, I'm gonna do first trace re-ranker, and I'm gonna come up with, let's say, 100 documents, right? Elastic gave me 100 documents. But based on the question, I want an unsupervised model to re-rank these semantically. So what does that mean? There's a cool example of this. So let's say that you went through hybrid search. And by the way, I think I took out the retriever slide because I just had limited time. But let's say that you asked the question, when was total eclipse of the heart done, right? And the top 3 results, and it can't answer. In a retrieval augmented generation, it's gonna say, I don't know, because the answer is not there. Well, what if we went through semantic re-ranking? What would end up happening is you would say the original question, give it all the results, and you would say, oh, well, when the total eclipse of the heart was done, it would say based on that, it would re-rank it to the top, and that's what you would set to your context window, right? This is limited in scale. So if you think about BM25, hundreds and thousands of millions of rankers, right? It's an algorithm. When you go to LTR, you're at about 100,000. This is at 100. Okay, so you can't just say, let me just skip everything. Why can't, there was a customer asked me this, why don't you just skip everything and just do this? This has a scale limitation. This is not an Elasticsearch scale limitation. This is a semantic re-ranker models limitation. 100 documents. So go through your practice of however you rank your documents, get the top 100, feed it into the sucker, and it'll semantically re-rank it. In case you don't know, all the code examples, this is engineering-led. This is not Elasticsearch, our document space. This is an engineering-led page. I contribute to it. By the way, we were talking about chunks. I just published an article 2 weeks ago about facts surrounding chunks, and it also actually uses an algorithm. It kind of does what you were exactly talking about. I was impressed. I basically look at the distance between 2 paragraphs and see how close they are, and then I chunk them together. So I have an article there, so I contribute to it. Many engineers contribute to it, and there's examples. So you don't have to know everything I said here. There's a really good one, the caching layer by Jeff Vestal. A lot of good folks here. That's it.